welcome everyone. My name is Zahra Sarpana Surkui. I'm a PhD student starting my second year at the University of British Columbia under the supervision of Professor Mohammad Zarifi. Unfortunately, my colleague Dr. Dima Kilani couldn't attend this session in person, so the decision was on me to present her work on behalf of her. The work is on a low-power AI hardware accelerator microwave-based ice detection. The topics that I'm going to cover in this session is on motivation and background, hardware accelerator for microwave-based ice detection, simulation results on 22 nanometer fully depleted silicon on insulator global foundries technology, and conclude. No one can deny the importance of artificial intelligence and neural network in today's life, especially when it comes to the practical applications. When you have a sensor, you need to collect the data using the sensor, send it to the cloud, sending to the cloud to do the feature extraction, computational algorithms, data mining, and so on in order to do the decision making. But there is one disadvantage in this approach, which is the requirement of sending data to the cloud and to the server in order to perform the computation regarding the artificial intelligence. One solution to this disadvantage is the utilization of edge AI, which basically means to have these artificial or ANN algorithms next to the sensor, where you can do these algorithms close to the sensor. You don't require to send a large amount of data to the accelerator, to the server, and we can do it next to the sensor in order to do the decision making. And the good point here is that it will be low power and you require less time in order to train the model and do decision making. What our group does in Omega Lab is that we basically fabricate and design and work with microwave ring resonators. To be briefly about how this sensor works, for example, this special sensor that you can see here, you expect that when you apply different signals with different frequencies, you expect that no signal can pass through this transmission line because there is a discontinuity. But because there is a ring here, based on the length of the ring, that can perform as an RLC resonance circuit in very special frequency, which gives you a signal transfer in a very specific frequency. Now, when you introduce a specific material to this very special gap here, you can alter the capacity of the effect of the gap, which basically results in a shift in the resonance frequency and the amplitude. So that is basically how we perform sensing in our. Talking about the microwave ring resonator sensors and artificial neural networks, you can here see two different works utilizing these ring resonators for wirelessly detecting ice accumulation, which can cause hazards, especially on the wings of the airplanes or on the wind turbines in cold places. And for liquid characterization, where they require to send a big amount of data, let's say, on the server in order to do the computation. So in order to reduce the time and have a low power implementation, a hardware implementation is required, which leads us to this work of my colleague here. Here you can see the block diagram of the work, where a microwave split ring resonator or SRR is used in order to sense the data, and only 4 points is selected, and the data, the scattering S21 parameter, the RF data, is sent to a cover detector in order to change it to measurable DC voltage. And these voltages are sent to a hardware implemented ANN with one hidden layer on an IC chip in order to classify between ice, air, water, and air. Air basically is the bare resonator. Here you can observe the simulation results done in the ANSYS HFSS where a ring resonator is designed to perform the resonance on 5.1 gigahertz, and different chunks of material is introduced based on their relative permittivity and loss tangent in order to see the variation in the frequency, resonance frequency and amplitude. So you can see different thickness of ice and air and water characteristics are applied to see the results. Based on these results, 4 specific points were selected in an optimum way to be fed into the neural net. And how they decided to choose these 4 points is fully presented in another previous work of the author. And here, the flow chart of the decision on the machine learning model is shown. Basically, the requirement is to have the highest achievable accuracy. So if the model gives 402 samples were selected, 80% of this data was used to train the model and 20% was used to test the model. If the model has good accuracy, it is selected. If not, the model is modified. And finally, a model with 98.8% accuracy was selected. Here you can see a true and target class of the fusion matrix here. And this is done in MATLAB software. Using the MATLAB software, the weight required to have to implement the ANN is achieved. And the main operation of implementing a neural network, as you confirm, is the weight multiplied by the input. But how we can implement this multiplication and addition in hardware? Let's consider this PMOS current mode circuit here, which the output current is replicated by input current based on the size of the output transistor or the ratio of these two transistors. So if we could select the width or size of the output transistor as a, let's say, V times to the size of the first transistor, we could basically implement the V times the input. But this is only one unit cell. What if we wanted to have, we should have multiple addition, multiplication and addition. The solution to this is to introduce a crossbar of PMOS current mode circuit, where the first those 4 points voltages should be fed to a voltage to current converter in order to have the current to be fed into each of these PMOS current mode circuits. And in the output, you will have the I out, which is basically the V times to the input current. There is another problem here. When the output, when the weights extracted from MATLAB was achieved, there were some negative weights. So how we can implement the negative weights in hardware? The solution to this problem was to have to add another crossbar here in order to shift with minimum width, to apply a shift with the minimum width to it. Since we are adding this shift, now we need to get rid of this effect. And the solution to how to get rid of that added shift was using an NMOS current. When we use the NMOS current, the output current is going to be synced down. So what we have in the output is the, let's say, the current of the first node of the hidden layer is going to be subtracted by the current of the fourth added layer, and we have the subtraction result. This result should be fed to a ReLU activation function, again in hardware implementation. It is basically fed to a compressor, and this compressor will decide if the current is coming is greater than a reference value, it will pass that current. Otherwise, the output current will be 0. So to test this, and all these concepts should be repeated again after hidden layer in order to have the output results, in order to classify ice, air, and water. To test this approach, a simulation was done in cadence in 22 nanometer FDSOI, where two examples you can observe here that in the first one, the current of the first node of the hidden layer was less than the current of the fourth crossbar, and the result was 0, result coming from the activation roller function. And when it was greater than the fourth crossbar, the subtraction is the output. When the two table here shows the results from actual output, which basically means the output from the MATLAB, and expected output, which is coming from this simulation in cadence. And you can observe the difference or the error is 0.068, which is a low value. But the accuracy achieved from this hardware implementation is 96.5%. Although the paper was done on the simulation, the work didn't stop and it is in progress. Here you can see the picture of the designed chip and fabricated chip, which is still under progress and under test on 22 nanometer. So a work on AI hardware accelerator was introduced for ice accumulation detection, and the accuracy achieved by the MATLAB was 98.8%. The accuracy achieved by the simulation was 96.5%. And the sensor was a microwave split ring resonator. Thank you for your attention.